Okay, the next one I'll do for you guys is the carboxylic acid. What you're looking for in the carboxylic acid is a carbon with a carbonyl group attached to it and a hydroxyl group attached to it. And that's going to be an RCOOH, and the ending that you're going to give that is an oic acid for the molecule. So if you had heptane, you would forget the E at the end of it and say heptanoic acid instead. And if it's an alkane, it's heptanoic acid. If it's an alkene, it would be heptenoic acid. And if it's an alkyne, it would be heptinoic acid. So we'll do 3 examples and they get harder, and this is a crazy one over here, but we do an isomer review as well. So we'll get up to it. We'll work up to it. When you're numbering these, you're always going to number the carbon with the carboxylic acid as carbon number 1, because it'll always be at the end to have both of those substituents bonded to it, just like the aldehyde. So it'll be 1, 2, 3, and don't forget that's just a bond to chlorine at the end here. So it would be a AN because it's all single bonds, and oic acid because of the COOH. And the side chain is a 3-chloro. Our next one is 1. We could go 2, 3, 4, or we could go 2, 3, 4, or we could go even bigger to a 5-carbon molecule. So that would be a pent, AN for single bonds, and oic acid for the functional group. And then we have 2 side chains, a 3-methyl and a 2-ethyl. So the 2-ethyl will win alphabetically and numerically. So it would go first 2-ethyl, 3-methyl, pentanoic acid. And then finally, we have this molecule over here, a bit of a beast. It's always going to be carbon number 1. So it'll look scary at the beginning, but you just go through and number your carbons. That's the first step to any of them, and don't panic. 6, 7. Yep, so that's a hept. We have a double bond on carbon number 4, so it makes the heptane turn into heptene at carbon number 4. We would drop the E at the end and replace it with oic acid, and that's our backbone. Hept for 7 carbons, 4 for the double bond, En for the double bond of an alkane, and oic acid for the functional group COOH. Then we just have these chloro molecules, and you notice their arrangement. They're not on opposite sides. They're on the same side of the double bond in reference to the carbon backbone. So that's a cis arrangement. I could draw the trans arrangement of this over here, just so you could see. When I hit my double bond, it would go down, and the chlorines would be on opposite sides. But because they're on the same side, it's a cis. On carbon number 4 and 5, we get the chloro. We have 2 of them, so there should be a di in front of it. And altogether, that makes this name be a cis 4,5-dichloro hept 4-enoic acid. So you're only going to do that cis-trans thing. Sorry, I don't know if I've said this in class, but I should say it now. You're only going to do that cis-trans things for a double bond alkene. That's with 2 substituents on it that are unsimilar, and they could be on the same side for cis, opposite side for trans. You don't have to do it for alkane because there's no same side, opposite side, and you don't have to do it for an alkyne, just the alkenes.